The quest for fusion. The process that creates the sun's energy is called nuclear fusion. In normal circumstances, the positively charged nuclei of atoms repel each other very strongly. In the centers of stars such as the sun, however, the pressure and heat are so intense that the nuclei overcome this repulsion and fuse together to form heavier atoms, liberating a tremendous amount of energy in the process. The radiation from the sun's nuclear fusion is the source of almost all energy on Earth. However, only a tiny fraction of that energy is ever captured. Instead of simply trying to harvest solar energy, what if it were possible to build a mini-sun right here on Earth and produce fusion energy directly in a reactor? Success would mean a clean, almost limitless source of energy. Nuclear fusion should not be confused with nuclear fission, the process currently used in nuclear power plants around the world. In a fission reaction, energy is obtained from splitting large, heavy atoms into smaller ones. Nuclear fusion has some clear advantages over nuclear fission. The fuel sources for fission reactions, uranium or plutonium, are highly hazardous materials and must be handled carefully for both health and security reasons. In contrast, the fuel source for fusion, hydrogen obtained from water, is harmless. In addition, with fission there is the possibility that the reaction will get out of control and lead to a serious environmental disaster. On the other hand, a fusion reaction will slow down and stop as soon as the energy input is cut off. In other words, fusion could be both clean and safe. But nature will not give up her ultimate power source without a fight. The path to creating a sustainable fusion reaction is fraught with technological challenges. The first obstacle to overcome is that producing a fusion reaction takes a tremendous input of energy. In the sun's core, fusion occurs at 15 million degrees Celsius. On Earth, however, it takes approximately 100 million degrees because it is impossible to reproduce the enormous pressure in the center of the sun. Moreover, even if a temperature of 100 million degrees were achieved, it is difficult to build a machine that can withstand that intense heat for more than a few seconds. Despite these challenges, researchers have succeeded in producing fusion reactions on Earth. The first controlled fusion reaction was produced in 1964 using a technique informally called laser fusion, in which lasers compress and heat materials enough to cause fusion to occur. Although the scale was small, these early experiments showed that fusion was at least possible. The first real progress, however, occurred with the construction of the first tokamak reactor in the Soviet Union in the late 1960s. In a tokamak reactor, gas is pumped into a donut-shaped chamber. Electricity is passed through the whole of the donut to turn the gas into a highly energized charged form called a plasma. At the same time, powerful magnetic coils around the outside of the chamber squeeze the charged plasma to extreme pressures, while radio waves and microwaves heat it to a temperature at which fusion can occur. Over the decades, a greater understanding of physics as well as improvements in engineering and materials science have allowed researchers to modify and refine the tokamak design. In the 1970s, a reaction lasting microseconds and producing milliwatts of power was considered a success. By the 1990s, a reaction lasting 1 second and producing 16 megawatts of electricity was achieved. At the present time, a huge tokamak reactor capable of sustaining a reaction for minutes is being constructed in France. The facility, called ITER, will produce more energy than is put into it, an important step on the path to building an actual nuclear fusion power plant. The ultimate goal, of course, is a working fusion power plant that can sustain a reaction for months at a time. Improvements in computer modeling are currently being tested to improve the reactor geometry. Additionally, there is ongoing research into using liquid metal to house the reaction, as this design might be better at coping with the extreme temperatures inside the reactor. It is also hoped that new and powerful superconducting magnets will lead to smaller, more efficient reactors. Should this research prove successful, the first commercial fusion plants might start operation within the next few decades.